I got my general response because I got my roots. I know it either has to be critically damped, over-damped, or under-damped. These solutions are just, I don't care. You just take them and you shove them right in. We don't care about that. That's a standard process here. So then, here we go. Here's where we got to really pay attention now. The details get deep here. You got to determine the voltage or the current before the switch is thrown. When that switch is thrown, we know that V0 plus for these two have to be exactly the same. That determines one of the constants right there. We're going to force that on our general response. Second of all, we need the derivative term. How do I get the derivative term? I got to go to the first two-order equation. Now, in general, it's equation 2. It's not always that way. In fact, I'm going to show you right away that first circuit right there, you can't do that. And you'll see it gets trickier. So we want to make sure that you're aware that that's a possibility. And the reason why that one becomes a possibility is because I'm trying to give you nice numbers to work with. And if I give you nice numbers, then things can get real ugly real quick. And so that's the problem. And then I got to determine my constants. What constants do I need? I need A1 and A2. I need A1 and A2. So what does that mean? I got to set up two equations, two unknowns. How do I set them up? Well, first, when I look at, once I get these two variables here, then I'm just applying these conditions to these equations. By the way, I'm not giving you this. This is just to open it up so that you can see the details. If I'm critically damped, I look at 0 plus. What do? Here's my critical response. So what do? I set t equal to 0, and that's what I get. By the way, this critical constant at 0 plus is typically the V constant. But we'll wait to see here. Then I got to take the derivative of this term. Here I go. I take the derivative of this. Here's the derivative. And then I set t equal to 0, and I get that. So now, these are my two equations to solve A1 and A2. So if I know this guy, I know A2, I plug it into here, and then I can solve for A1. The same thing happens for overdamp. Here's my overdamp equation. At t equal to 0, it looks like this. If I take the derivative of this equation, you can see I break down the s's, so then I get that equation. Here's my two equations, two unknowns. And you can see this is a 2x2 problem. Because I have two equations, two unknowns. Here, this determines that, so that's fast. This one's not so fast typically. So here's my underdamp. I take t equal to 0 plus, I get that. Then I take the derivative of this huge mess. I set t equal to 0, I got that. Okay, so it's just this process here. So it's almost like turn off the brain, start turning the crank. Right? It's a mathematical process now. You've done all of the physics of the circuit now. Here, we're just trying to mathematically crank this thing up.